So our next topic is the topic of the geometric and negative binomial distributions, two more discrete probability distributions. And in this video, we're going to look at the theory behind the geometric distribution, and we'll build this topic up over the next few videos. So I think the best way to talk about this distribution is actually through this game, which I know to be called Frustration, although I've been told that there are other names for this game. And I do think it is one of the most frustrating games if you've ever played it. The concept is that you need to get your counter around the board in a full circle and then into your home bases, which are the bits in the spokes leading up to the center, using the dice to dictate how many spaces you can move. But the frustrating bit is you can't start the game until you roll a 6, because the 6 allows you to move one of your counters from its start, which are the corner bits, into the game. Now, of course, I'm sure you can imagine that there are situations, if you've never played this game before, where other people are merrily on their way, doing quite well, seeing lots of 6s pop out, they've got counters all over the place, and you are still stuck trying to roll that 6. We could ask the question, what is the probability that it takes you up to your 4th attempt at this before you roll that 6? And that is perhaps a probability we might be interested in. Maybe not to calculate the game so much, because who's actually sitting down doing maths when you're playing a game like this? But in other situations where you would be interested in knowing what are the chances it's going to take you until a certain number of attempts to win something or to gain something. So let's have a look at that. It is fairly intuitive, this distribution, I think. So what's the probability that you roll your first 6 on your 4th attempt? Have a go based on what you think will happen to that probability. I think it's as straightforward as you think it will be. So assuming you've had a little go, you should pause the video. Let's talk it through. So if you get your first 6 on the 4th attempt, that means the first 3 attempts weren't 6s. So what was that probability? Well, let's assume it's a fair dice for a start. The probability of getting a 6 is a 6th, assuming it's fair. And the probability of not getting a 6 is the remaining probability, so 5, 6. In which case you failed the first 3 times and then succeeded. So we have got 5 6 times by itself to the power of 3. That's what that would be. Multiplied to your 1 success, your 1/6, which comes out to be 125 over 1295. And it is that intuitive, and I think that's a strength of this distribution, because it doesn't do anything too bizarre, but does actually describe a situation that would make sense to us. So let's look to generalize this a little bit then. For an event with a particular probability, and that probability does have to be constant, we want to know what's the probability of it occurring on an unknown number, so that we can generalize as much as possible. So the x attempt. Well, that would mean that you have failed 1 less than x times, and then C1 probability of success. So that's P for that actual time you succeed, and then 1 minus P, the probability of failing, x minus 1 times. So all of the attempts leading up to that final one are fails. Again, hopefully that feels fairly intuitive to you, and don't forget all of these probability formulae, they're recorded in your formula book. Another thing we might want to look at is what's the probability of being less than or equal to that value. We like our regions. We're not always so persuaded by just having a single probability. We do like our regions. So let's have a look at that. We could succeed on the first attempt, on the second attempt, on the third attempt, all the way up to the x attempt. Notice this distribution doesn't start from 0 because you have to have at least 1 attempt at something. So we have the probability that x equals 1, plus the probability that x equals 2, plus the probability that x equals 3, all the way up to the probability that x equals x. Well, if you succeed on the first time, you don't fail, so you'll just have a 1 probability. If you succeed on the second attempt, you failed once and then succeeded. If you succeed on the third attempt, you failed twice, 1 minus p squared, and then succeeded, and we would carry on. Again, pause the video for a second and have a think about what that looks like. That should look like something, and your clue is in the name of this distribution. So assuming you paused the video and had a little look at this, I hope you spotted that this is a particular sequence, and like I said, the clue is in the name. It is actually a geometric sequence, starting at p, so a equaling p, and with a common ratio of 1 minus p. And we're adding up, so we can just look at the sum. This is the sum of the first x terms because we're trying to get up to x attempts. So I can write that as the sum from v, I don't know why I used that, but anyway, equaling 1 up to x of the probabilities, of course, because we're adding up each individual one. And then if you use the sum for the geometric, it's a lots of 1 minus r to the n over 1 minus r. So here we've got p as a, 1 minus r, which is 1 minus p to the number of trials, which is x, over 1 minus p. And of course, that could do with some developing. So the bottom sorts itself out to p, and then those p's on the top and the bottom of the fraction cancel, and we're left with the probability that x is less than or equal to x is 1 minus the failure rate to the power of x, which maybe doesn't feel quite so intuitive, but is obvious, I think, from looking at the creating the formula in the way that we have. So not always immediately obvious, but certainly verifiable using the algebra. So in the next video, we're going to have a look at some questions that use these two formula, and then we'll go through and look at hypothesis testing and goodness of fit attached to this.